All right, hey everybody. I'm going to do a few more practice problems here. This is also from slideshow 16. We're now on page 55, which includes 3 practice problems for indirect derivation. I'm going to move a little bit more quickly now, but feel free to pause the video if things are going a little bit too fast for you. All right, so the first problem we're going to work on is this one. It's got as premise 1, not P or Q, and then we're going to try to show not Q. Now, you might notice that if you're looking at the rule sheet, you might notice that on the right-hand column, there's a rule called not or out that would make this problem very, very simple. That is, you could just do the following. You could say not Q from 1 by not or out. And there's nothing wrong with that. That's perfectly acceptable move. But what I'm going to try to show here, sorry, let me finish it up here. So direct derivation, cancel, and box. And again, I'm just going to do the boxes like that now just to save a bit of time. There's nothing wrong with that, but it turns out not or out is a rule we don't really need. In fact, we can finish this proof just using indirect derivation. So that's what I want to show you how to do, because it will help us understand how indirect derivation works. So let's go ahead and write down the premises again. Not P or Q, and we want to show not Q. And of course we notate our premises there. Now if we're doing indirect derivation, we're allowed to assume something again, just like with conditional derivation, but in this case we assume what we're going to call the opposite. We either assume the unnegated formula or the negated formula. So in this case I'm going to assume Q, the opposite of not Q. And then we try to show a contradiction. And remember, we've got this special sign, this special X sign for a contradiction. Okay, how are we going to do this? And again, how are we going to do this without using the not or out rule? We want to see if we can do it without that rule. Well, here's the basic idea. We know that Q is true. So from or in, we know that P or Q. That is, we know that anything or Q is true. That comes from line 3 by or in. If that's confusing, go ahead and look again at the or in rule and make sure you understand why that is. But now look, we've got a contradiction. We've got P or Q in line 5, and we've got the negation of that very formula, the negation of P or Q in line 1. That's a contradiction. So we just introduce it, 1 and 5, by contradiction in. And so we've directly derived a contradiction. And so we indirectly derived not Q. That is, the assumption that Q led to something that is impossible, a contradiction. So we know that Q can't be true. That is, not Q must be true. So we did an indirect derivation for not Q. And that's how you can prove that, or derive that rather, without using not or out. And it actually tells us a little bit about how to understand what not or out is doing. Not or out is a rule we don't really need, because anytime we needed it, we could always just go through this little step here, these 6 steps here that we just went through. Not or out just saves us some time. It says, hey, we could always do this, so we're just going to save ourselves some time by making a rule that allows us to sort of skip some steps. All right, let's try a few more indirect derivation examples. This is example 2 on page 55. So premise 1, P and Q, and then the conclusion, is show not P, arrow not Q. Okay, so we notate here. This is our premise. And now we have to figure out what to do. Now, you might be tempted to try conditional derivation here, but remember you can't, because conditional derivation only works when your main connective of your show line is an arrow. And in this case, our main connective is actually a not. But we can do indirect derivation. We get to assume the opposite, P, arrow, not Q, and then try to show a contradiction. And here we can get it pretty easily. From line 1, we can get P. That's from line 1 by and out. From 3 and 5 now we can get not Q by arrow out. And not Q contradicts Q, which we can get by doing AND out. That comes from line 1 by AND out. So we just have to introduce that contradiction officially. We say lines 6 and 7 is where the contradiction is. That's our contradiction in rule. So we've directly derived a contradiction, which means we've indirectly derived what we set out to show. Again, I'm moving a little bit quicker here, but feel free to pause the video or go back if you're at all confused. Just going to get a new sheet of paper here. Maybe. All right. So 2 more examples we're going to do. Example 3, this is example 3 on page 55. Oops, let me make sure that's lined up there. There we go. So the premise, just one premise, says if P, then if Q, then not P. And we want to show, therefore, if P, then not Q. So we've got our premise and our show line. Now what should we do here? Notice that in contrast to the last case we just saw, the main connective of our show line here really is a conditional. So I recommend you always try conditional derivation if it's available. And since our main connective is an arrow, it is available, so we're going to assume P, and then try to show not Q. Okay, so how are we going to do that? Well, here's where we could use indirect derivation, and I think it ends up being useful in this case. It's not strictly speaking required, but it is useful. How would we set this up to show not Q as an indirect derivation? Well, we assume Q, and then try to show a contradiction. And notice where we are. If we can show a contradiction, we'll have shown not Q, which means we'll have shown P arrow not Q. So all we need to do now is find a contradiction using our available lines. That is our premise and our 2 assumptions. And hopefully you can see how that's going to go. We can just do a series of arrow out moves. So line 1 and 3, arrow out gives us Q arrow not P. Now from line 5 and 7 we can do arrow out again to get not P. Oops, I'm going off the screen there a little bit. There we go. And we now have a contradiction. We've got P in line 3 and not P in line 8. So 3, 8, contradiction in. All right, so our proof's done. We've directly derived a contradiction, which means we indirectly derived not Q, which means we conditionally derived P arrow not Q. And so we're done with our proof. The last problem I want to do in this video, move up a little bit here, is an example of a strategy that's good to employ in certain situations. And this is actually on page 56 now of slideshow 16. And here's the problem. Suppose we got as a premise not P arrow Q, and we want to show P or Q. So it's always a good idea, if you see a show line that has as its main connective an or, to try indirect derivation. And we'll see why here. It's because the assumption you get in that case is especially useful. So what do we get to assume if we're going to try indirect derivation? Well, the negation of this, not P or Q. And remember, the parentheses are important because we want to negate the entire show line, not just part of it. So we assume that. And then we're going to try to show a contradiction. Now we should try to do something with our assumption, and notice that our assumption is a negated or claim, a negated disjunction. And that's especially useful because we can use that rule we talked about at the beginning of this video, not or out. Not or out says from this I can get not P or I can get not Q. I'm going to go ahead and get both of them. So not P comes from line 3 by not or out. And we also get not Q from line 3 by not or out. Now I hope you can see it's going to be pretty easy to get a contradiction. From line 1 and 5 by arrow out we can get Q. And now we have a contradiction, Q and not Q, in lines 6 and 7. So we just write that down, oops, 6, 7, contradiction in. So we've directly derived a contradiction, which means we indirectly derived P or Q. And this strategy is general in the following sense. It's always a good idea to try indirect derivation if your show line is an OR, if the main connector of your show line is an OR, because the assumption you get is especially useful given the not or out rule. All right, that's all for this video. Again, let me know if you have any questions.